and before that we discuss electromagnetic induction. So now today we will start new topic, that is optics, very important topic. So let's start. So what we can observe contains the wavelength of this range. Okay, so what we can observe from our eye, that is having wavelength of 400 nanometer to 700 nanometer. So whole radiation what we have is if there is less space, I am writing it this way. RA stands for radio, micro, infrared, visible, ultraviolet, X-ray, gamma, cosmic. And as you go from cosmic to radio wave, wavelength increases. So here we are discussing about visible spectrum, which is from 400 nanometer to 700 nanometer. So as what is written, the sensitivity of individual observer may vary, but the human can typically observe radiation with the wavelength from 4000 nanometer to 7000 nanometer. And the source of that radiation, most familiar source, is sun. So we get all the radiation from sun, but that will be containing all the possible wavelength what I am discussing here. But in that our eyes are sensitive for a particular spectrum that starts from 400 nanometer to 700 nanometer. Okay, now so that debate went on for decade, whether light is particle or light is wave. So we get some observation where light behaves as wave, and some observation which can be easily justified if we consider the behavior of light as particle. Like photoelectric effect, light behaves as particle. Interference, polarization, light behaves as wave. So we can say that light is having dual nature, and it behaves as particle as well as wave. So wave nature we will talk about later, right? So differentiation between wave nature and particle nature, that we will talk later. Right now we will consider light as ray or combination of rays. So we start the topic with the law of reflection. First we will deal with reflection, then we will talk about refraction. So we are considering a ray falling on mirror. So this way incident ray falls on this mirror and gets reflected. So first law of reflection is that incoming ray or incident ray, outgoing ray, that is emergent ray, and normal to the mirror or reflecting surface at the point of incident, they all must lie on the same plane. So incident ray, emergent ray, and normal to the surface, they all must lie on the same plane. So this one emergent ray, this one incident ray, and the normal to the surface at point of incident. So perpendicular to the surface, this is normal. So they all must lie on the same plane. This is first law. And the second law is the angle made by incident ray with the normal and angle made by emergent ray with the normal, they must be same. So if I assume this to be angle of incidence I and this is angle of reflection R, then angle I must be equal to angle R. So these are the two laws we will use for every situation where we want to find the reflection of ray or wherever we want to find out the image of a particular object. So whether we have a curved surface, flat surface, for any surface, these are the two laws we need to follow, right? Now So I hope these two laws are clear. So what we just discussed, rays coming and falling at this particular point on mirror. So this is mirror, and after reflection it goes like this. So this is incident ray, and this is emergent ray. So if incident ray makes angle I, then we have just seen that emergent ray will also make angle I. R is equal to I, I am directly writing. So as you can see that initially the incident ray was traveling in this direction, and then what happens, instead of coming this side of mirror, it gets reflected. So as it gets reflected, it changes its direction. So we need to find out how much ray got deviated. So this is called deviation. So deviation is represented by this del. And if you look at this one, this total angle is 180 degree. Out of that 180 degree, you need to subtract this angle to get del. So del is equal to pi minus 2i. So if I want to draw variation, if I want to plot the variation at I is equal to 0, I can see deviation is 180 degree. Okay, so point will be somewhere here. That means if ray is falling perpendicular to the surface, if incident ray falls normal to the surface, after reflection it will retrace its path, it will go like this. So it has suffered 180 degree deviation. And then if I take another extreme value of angle of incidence, so this is for I is equal to 0. Now for I is equal to pi by 2, that means almost grazing the surface. So a ray falls here, almost grazing the surface. It goes almost like this. So now you can see that it was going in towards right, and it is still going towards right. So there is no deviation caused. So in this case, when angle is pi by 2, then there is no deviation. In this formula, if you see, if I substitute pi by 2, this 2 and this 2 will get cancelled out, and we are getting deviation 0. So we are getting deviation 0 for I is equal to pi by 2, and the value of deviation will be maximum when angle of incidence is 0. Okay, so this is an important curve, and keep this point in mind that deviation is coming. Linear with angle of incidence. So this is the expression for deviation. Now look at this one. Ray is falling at an angle I, and it is getting reflected at an angle I, this way. So now what I do, I rotate incident ray by an angle theta. So if I rotate this by an angle theta, so ray will be falling, making lesser angle with normal, as you can see in the diagram. So ray is now falling this way. As this angle is less, so angle of reflection has to be less. So I reduce the angle of incidence to say some theta or say some alpha. So this angle will also become alpha. That means if I rotate ray in this direction by an angle theta, then a reflected ray gets rotated by an angle theta this direction. So conclusion is if incident ray is rotated through an angle theta, the reflected ray gets rotated by angle theta, but in opposite sense. So you are rotating it in clockwise, and here you can see that this reflected gets rotated by same angle but in anti-clockwise. So here we are getting anti-clockwise rotation, and here you rotated it in clockwise direction, clockwise rotation. So sense will be opposite, but the magnitude will be same. So it will also get rotated by angle theta. Okay, so this is first point. Now let's see second point. So instead of rotating ray by angle theta, what happens when I rotate mirror by an angle theta? So in the diagram I rotated mirror by an angle theta. So let this be the new location of mirror. So mirror getting rotated by theta. Earlier mirror was like this. So as mirror get rotated by theta, its normal will also get rotated by same angle theta in the same sense. So now this angle will be theta. Earlier the incident ray, let make an angle I, angle of incidence, and reflected. So this was I and this was I. Now we are keeping incident ray fixed and we just rotated mirror, normal got rotated, and the angle made by incident with new normal is I plus theta. That means reflected, new reflected ray will also make with the new normal, new reflected ray, this angle must be equal to I plus theta, law of reflection. So I want to see how much it got rotated. If you see it carefully, then with new normal this is I plus theta, and this is theta. So with old normal it is making I plus 2 theta. Earlier with the old normal it was making angle I, So how much is the change in angle? Change in angle minus I plus I, they will cancel each other, we are getting 2 theta. So the point here is, if mirror gets rotated by theta, the reflected ray gets rotated by 2 theta. But in the same sense, so you rotated mirror in clockwise direction, and you can see that ray also got rotated in clockwise direction. So sense is same, angle has become, or angle is 2 theta, sense is same in same sense. Previous case in opposite sense. So when you are rotating ray towards normal, the reflected ray will also come towards normal. If you are rotating ray away from normal, then reflected ray will go away from normal. Sense will be opposite. While in this situation, if mirror gets rotated in clockwise direction, reflected ray will also get rotated in clockwise direction, but the angle will be 2 theta. If you rotate mirror in opposite sense, if I rotate mirror this way, then this ray will get rotated by 2 theta in opposite direction. So you have to be little careful with the direction. So if I say we have one situation, let this angle be some 60 degree. I rotate ray in this direction by 5 degree, and I rotate mirror in opposite direction, say 10 degree. How much incident ray will get rotated? So because of rotation of ray, the reflected ray will get rotated by 5 degree in opposite sense. So you are rotating it in clockwise, then it will be anti-clockwise, anti-clock 5 degree, and then as you are rotating mirror by 10 degree, then it will get further rotated by 2 times 10 degree. So 2 into 10 degree in the same direction, anti-clock. So this is anti-clock, anti-clock. So how much reflected ray will get rotated? 25 degree, and it is in anti-clock. So earlier with normal, the ray was making 60 degree, because when you rotate mirror, obviously the normal will get rotated. So if I assume this to be y-axis in this direction, it will get rotated by 25 degree. So with old normal or new normal, you can find out at what angle it will come out. So this example I hope is clear. So two things we have discussed: what happens when ray gets rotated and what happens when mirror gets rotated, right? Let's see next one. So a ray is falling on a mirror M1, and after falling on mirror M1 it gets reflected and falls on mirror 2, and then finally comes out. So question is, find deviation of ray after two reflections. So we need to find out how much ray is getting deviated. After this one, ray will fall, see somewhere here. I am drawing rough diagram, and then if I have the normal of this mirror, I can use law of reflection and find out how this ray will go after reflection. So this is what I can see. So incident ray was traveling in this direction and reflected ray is traveling in this direction, and this much is the deviation. So if I say this angle is I, it is not given. Let's check how much deviation we get. So I'll assume that this angle is I. If this angle is I, this angle of reflection has to be I. So this angle is 90 minus I. Let this angle be some beta. So what I can write, theta plus beta plus 90 minus I is equal to 180. That means beta is equal to, this is 90 plus I minus theta. If I assume this angle to be alpha, so alpha is equal to 90 minus beta. Alpha is equal to 90 minus beta. I can substitute beta value of beta here. So 90 minus 90 plus I minus theta. 90 will get cancelled out. I can see theta minus I. So alpha is coming theta minus I. If this angle is alpha, this angle has to be alpha, and this is external angle which will be equal to sum of two internal angle. So deviation is 2 times I plus 2 times alpha. If I substitute value of alpha here, that is theta minus I, we are getting deviation as 2 theta. So you can see that this deviation what we are getting is independent of angle of incidence. So irrespective of angle of incidence, the deviation suffered by the ray after two reflection just depends on the angle between two mirrors. So whether it is falling on mirror 1 first and then mirror 2, or it is falling on mirror 2 first and then mirror 1, in both the cases after two reflection the deviation it suffers is del. So keep this point in mind, very useful point. Now let's see another situation. So we have got one ray, incident ray, and its unit vector is given to you. So incident ray unit vector you have, and normal to the surface also you have. So this n cap is also given to you. And question is, what is unit vector along a reflected ray? So find unit vector along reflected ray. So here EI stands for unit vector along incident wave, incident ray, n cap unit vector along normal to the mirror, so this one is mirror, and then E unit vector R is unit vector along reflected wave. So I hope all notations are clear. Now we want to find out ER in terms of EI and n cap. So first EI, incident ray unit vector. This will have two components, one parallel to the surface, so component of incident parallel to the surface, and another one is component of incident perpendicular to the surface. If I want to find out reflected wave unit vector, reflected ray unit vector, then if I resolve the component of this one, so its component will be like this. If I see the component of ER, component will be like this. So as you can see that this parallel remains same, perpendicular just gets reversed. So same parallel, but this gets reversed. So minus E incident perpendicular I can write for ER, and E parallel from here I can substitute, and I am getting E incident minus E incident perpendicular plus minus E incident perpendicular. This I can further simplify. E incident unit vector minus 2 times E incident perpendicular unit vector. So I require the component of this one in perpendicular direction. If I assume this angle to be I, then we can write its component in that direction is E I unit vector cos, that can be written E I unit vector dot n cap using dot product. So component of this one in that direction, and this is the magnitude, in that I'll add direction. So what is the direction of component which is perpendicular to the surface n cap? So with this magnitude I'll add this direction, I'll get EI perpendicular. So EI unit vector minus 2 times, this can be written EI dot n cap, then direction is n cap. So this is the formula for finding unit vector along reflected ray. If you have incident and you have normal to the surface, you can find out ER. So I hope this is clear how to find out ER. Let's take one example, then it will be more clear. So I'll erase this part. Example, I'm writing here itself so that we can see the application of this formula. A ray is falling on mirror along minus I minus j plus a. Whose normal unit vector is I plus j by root 2. Find unit vector along reflected ray. So you need to find out the unit vector along reflected ray. See, so I can remove this derivation and you will see the application of this formula. see. So first I'll try to find out the unit vector along incident, that is minus I plus j minus j plus k minus j plus k divided by root 3. I converted into unit vector, and we have normal unit vector, that is I plus j, it is already unit vector. So if I use these two values, then ER unit vector is equal to EI, that is minus I plus j minus I minus j plus k divided by root 3, and then 2 times EI dot n cap. So minus I minus j plus k by root 2. This we need to take dot product with the normal unit vector, which is I plus j by root 2, and after that I need to write normal unit vector, that is I plus j whole divided by root 2. Let's simplify this one. So minus I minus j plus k divided by root 3 minus, this is 3, and this root 2 when you multiply it will get cancelled out by 2, and then I dot I minus 1 j dot j minus 1 I plus j whole divided by root 3. So here I can see minus 2 and then plus 2, so plus 2 I plus j divided by root 3. This minus I'll take out, plus, and then minus I minus j plus k divided by root 3. This one is root 3 in bracket I plus j plus k. So the unit vector along reflected ray is coming in this direction. The unit vector we are getting is I plus j plus k divided by root 3. So this is the way we use this formula. So everything is given in 3-dimensional form, IJK form. We can find out reflected ray in IJK form. So I hope this example is clear. Let's take one more example. So I'll erase this one. We will see one more example. See, if I say there are two mutually perpendicular mirrors, So mirror 1 and mirror 2, and a ray is falling on this mirror, and then after falling here it falls on mirror 2. The diagram I am drawing is 2-dimensional, but ray can be 3-dimensional. Okay, so it will have ijk, and after reflection it will have ijk. So if I say there are two mutually perpendicular mirror and rays falling on one mirror, after two reflection you have to prove that ray will definitely emerge opposite to the incident. So there will be the deviation of 180 degree, I am saying. Okay, so if I assume that this is E incident, so finally when ray will emerge, I need to prove that it will be minus E incident So if ray is getting reflected from two mutually perpendicular mirror, you need to prove that ray will come anti-parallel. Okay. Or I can also ask, find the deviation between incident ray and emergent ray. Find deviation between incident ray and emergent ray. So if I take one mirror on xz plane and mirror 2 on yz plane, so this mirror 1 is on xz plane and this mirror 2 is on yz plane. And I am using generalized expression of angle of incidence. So if I call this as some ER unit vector prime, so ER unit vector prime will be equal to EI unit vector minus 2 times in bracket EI dot n cap. So let's first find out this. This is, look at this mirror. This mirror will have unit vector along y direction, so j cap I can write in place of n cap. So EI unit vector minus 2 times EI unit vector dot j cap. Then this behaves as incident ray for the second mirror whose unit vector is I cap. So same procedure I need to use to get this as reflected double dash, finally reflected ray. So ER double dash, this will be incident ray I can use this formula. ER dash will be equal to EI. I am substituting the value here. ER dash so this complete thing is EI, and then I need to do dot product with the n cap, and n cap for this surface is I cap, so I write I cap over here, and then I cap. Now nothing is left, I feel. So everything I have written. Let's see. So EI cap minus 2 times EI dot J cap minus, let's look at this one. This term I need to do dot product with I. Okay, so 2 times E incident dot I cap, and then plus 2 will give you 4, and then outside I have I. Okay, so here I'll write I. Then this will be 4. Look at this one, I dot J. So this with this one will give you 4, and then here we have E J unit vector dot I unit vector. So this one dot this one I have written here, this one dot this one I am writing, out of that this is 2, this will give you 4, and then outside I. So this term will become 0. So what we have here is this unit vector, okay, dot I J cap. So if I assume that EI unit vector is having some x component, or A along x direction I plus B along y direction J, then in that situation look at this one. So this is on xy plane. When I do dot product with J, this whole quantity dot product with J, yani EI dot J, when we are doing, then we are getting dy, and then we are putting J behind. So this whole term will be like this, and as we have 2 here, I'll put 2 here, then I'll get 2 here. Similarly for next term, look at this one. So 2 times Bx I cap. Next term I am getting, all these you can see with negative sign. So if I just write Ax I plus Byj minus next term is coming 2 byj, and then this term is coming 2 axj axi, and if I simplify the whole thing, I'm getting minus axi minus byj, and that is nothing but negative of e incident. The whole thing is coming negative of e incident. That means if this is ei, the one which is coming out will be minus ei. That means there will be 180 degree phase 180 degree deviation. So deviation suffered is 180 degree, and just now we proved if this angle is theta, so deviation suffered if two mirrors are at angle theta, then rays falling here, then falling here and coming out, this deviation we got 2 theta. So if this angle is 90 degree, then this angle will be 2 times 90 means 180 degree. We already proved this one. As I wanted to make you understand this procedure, I wrote each and everything. So though this method is lengthy, but if I add one more component and I place one more mirror, then it will be very difficult to decide by this method. So for 3 mirrors which are mutually perpendicular, the incident and the finite emergent ray after 3 reflection from these 3 mirrors which are kept mutually perpendicular deviation will be 180 degree. So in that case I need to write k also. So one more term will come that will have k. Then in this term there is one more thing added, that is minus czk. So 3 mirrors are there which are placed mutually perpendicular, and we are allowing ray to fall like this or in such a way so that ray gets reflected through all 3 mirrors. Then incident and reflected will have deviation, or incident will have deviation 180 degrees. So I hope this point is also clear. Let's move to next point, field view. So if I take one object here, in front of mirror, and I draw ray diagram, ray falling here getting reflected this way, and the ray falling here getting reflected this way, right? So the ray falling somewhere here will get reflected this way, and the ray falling somewhere here will get reflected this way. So this whole region is called field view. So observer in this region can observe the image of this object, but if an observer is outside this field view, he cannot see the image of this object in the mirror. Similarly, any observer here cannot see the image of this object in the mirror. So for observer to observe the image of object in the mirror, he has to be in field view. So to locate the region from where the image of object can be seen, we draw field view. So we just take 2 extreme point on the mirror, and with the help of that we draw field view. Okay, so to understand this concept, let's take one simple example. If I place object here on x-axis, say at 2, 0, and we have got mirror, this point is 4, 2, and this one is 4, 4, assume, and we have got one observer which goes along y-axis with 2 meter per second, and if I ask for how long observer can observe image of object in mirror. So what we require here is the field view. You see, the one which is falling here will be going like this. The one which is falling here is going like this. This angle must be equal to this angle, and the one which is falling here will be going like this. If I extend y-axis, you can see this is the field view. So intersection of path that observer follows with the field view will give duration or length for which image of object can be observed. So from this triangle and this triangle, I can find out the coordinate of this point. So if I write what I am getting, this height is 2, so 45 degrees, so this is 45 degree, this angle is 45, that means this length will be equal to this length. So this length is, what I can see is 4, that means this has to be 4, and this is already 2, that means coordinate of this point will be 0, 6. Same way I can find out this is equal to this one. So if I assume this distance to be something y, this is 4, so y by 4 will be equal to, this is height is 4 by 2, so 2 and y is equal to 8. So this itself is 8, and from here this is 4, that means coordinate of that point where the ray falling at this extreme of the mirror cuts the y-axis is 0, 12. So the gap of field view, now I'll remove each and everything, the gap of field view, this gap is coming 6 meter, and how long will it take for this observer to cover 6 meter with 2 meter per second? So time I require, distance I know 6 meter divided by speed meter per second, that means we are getting 3 seconds. So for 3 second duration only, observer can see the image of this object in the mirror. So I hope this concept of field view is clear. In the next class we will discuss few more problem on the field view, then we start tracing image of the given object, right? So I hope you enjoyed today's class. Thanks very much for watching.